Pode começar? Primeiramente, boa tarde a todos. Hoje nós vamos ver o colóquio do professor Leonardo, que é pesquisador do LHC, Laboratório de Instrumentação de Partículas de Portugal. Tá? O professor Nuno está aqui com a gente graças ao suporte do Campus Print, né? Eles nos ajudaram nisso, aparecendo aqui, parte internacional da UERJ. E o professor Nuno, atualmente ele está como investigador no LIP e também como investigador convidado também no Técnico em Lisboa, né? E ele tem PhD em Física pelo MIT. Tá? Nuno, obrigado mais uma vez. A plateia é sua. Obrigado.
Obrigado. Boa tarde a todos. Se calhar vou desligar aqui a luz, se estiver ok. Portanto, eu queria começar por agradecer então ao Sandro e às pessoas todas do departamento pela oportunidade e por me receberem cá estas semanas. E portanto o que eu tinha planeado fazer então hoje era dar-vos alguns highlights do LHC. Na verdade eu preparei os slides em inglês, portanto se calhar e vocês vão perceber melhor a minha pronúncia em inglês, se calhar se não se opuserem eu vou falar em inglês. Alguém se opõe a que eu fale em inglês? Está ok? É melhor, não é? Quer dizer que não estás a perceber o que eu estou a dizer? Fantástico. Sim, senhor. Muito bem. Ver se funciona. Funciona. So, I'd like to then start by recalling some ancient questions that we start asking ourselves a long time ago. And that we've come a long ways trying to answer them through the scientific method and with the employment of ever more sophisticated instruments. And with this, we started with this picture of a philosopher thinking about the universe, and we arrived to this other picture that illustrates the evolution of the universe. From the Big Bang all the way to nowadays. So now, one way in which we have to go back in time and to probe the early stages of the universe is through particle colliders. With ever-increasing collision energies, we go further back in time, where we can probe here the stages before the hadrons actually form, and we probe this so-called quark-gluon plasma that we'll discuss later, and further with higher energies, you can probe the structure of vacuum. So this is a picture, and which is a qualitative picture, but indeed we have something more useful, which is here this Lagrangian, this formula, that for it to become useful and to do calculations, you actually need to expand it. But in this short notation with these symbols, it's actually very convenient for us to see what the ingredients that come into play are. And so if you go line by line, you see that the first line there contains the dynamics of the bosons, of the force mediators. If you look at the second line instead, you have the interactions of these gauge bosons with the particle fermions, And in fact, up until 7 years ago, this was the part of this theory that was, directly tested, actually directly confirmed experimentally. But as you know, in 2012, we observed the scalar of the theory, so this that we call the Higgs, represented by phi here. And if you look at the last equation there, you have this term that includes the interactions of the Higgs with the gauge bosons. And here, in this last term, the Higgs potential actually contains the self-interactions of the Higgs, something that we are looking to, we haven't yet seen. And then, last but not least, in this third equation here, we have the interactions of the Higgs with the actual matter fermions. And this is at the core of the flavor sector of the standard model. And of course, this is the standard model, and perhaps there's something addition to it, and we're looking for that as well at the LHC. So in this other picture, now you'll recognize this. So this says the building blocks, so the so-called periodic table of the particles, where in the rightmost column there you have the bosons, the intermediary of the fundamental forces, and on the left you have the fermions. The fermions include the quarks, that are the ones that feel the strong force, and the leptons that do not. And as you can see, the fermions are organized somehow, for some reason, in three families, three copies, if you like, in three that we call fermion flavor families. Now, the standard model does not predict that there should be three. In fact, we do not know where there is three and not five, say. But as it happens, the standard model can accommodate what we have observed, and those are these three families. Now, in order to establish this picture, there was quite, over the last half of the last century, there's quite some developments. So the last particle here to be found is the heaviest one, the top. This was done at the Fermilab in 95 in Chicago. And now there's also the bottom quark. This again was found at Fermilab, and that was 40 years ago. And here I want to illustrate to you, how we actually see particles. What we have in this plot on the x-axis is the invariant mass, so of the final states that you're considering. In this case, a pair of muons. So you detect in your detector two muons with opposite charge. You compute the invariant mass, and then you have this picture, which shows you, continuous falling spectrum, and on top of it, a bump. And this bump is then the upsilon, which is a bound state of quark, anti-quark of big quarks. Right, so this was 40 years ago, and then if we fast forward to 2010, when we actually turn on the LHC machine, this is the picture that we got. So this is the equivalent picture. Again, you have on the x-axis the dimuon invariant mass spectrum. And again, you see here the upsilon, and in addition to that, you see various other resonances that are well known. So this, I don't know how many of you have seen this picture before. I'm very proud of this picture. I co-invented this picture with my colleagues at Purdue at the time, and I had the pleasure of showing them in the first international conference, main international conference after the turn of the LHC. And it's difficult for me to convey to you how exciting it was to get this picture, where we've been preparing the detector, putting up the machine, and then we turn it on, and you see this. And essentially, what this represents is the rediscovery of the standard model and the LHC, and it illustrates the capability of the detector to explore, huge or many orders of magnitude in terms of sensitivity. We have resolution for here as we have resolution for there and beyond. So this was exciting. Now this was at the start. It was almost a decade ago. Now, if we move to now, this is how this same picture looks like. And you see that the precision has, the resolution of this image increased considerably. You see the same signals, but with much better resolution. And so, this illustrates, the huge amount of data that we have and the quality, the richness of our data set. And then the question is, what can we and are we doing with this? And there's two things that we are doing. So one is measuring with precision the standard model, with ever-increasing precision. And the other thing that we're doing is to try to go beyond the standard model and find new structures in our data. Now, of course, in terms of new particles, the most famous one that has been found at the LHC and that all of you heard about was the Higgs boson. So this is not just any particle. This was the scalar particle of the theory, the only scalar particle that we have ever seen that is elementary, and that's the last building block of the standard model. The way we found it is, similar to as you did before for the big quark. So we have, a falling mass spectrum, in this case the diphoton, and then we have a bump there, right? So this is all great. This is for finding new particles. This is the most famous we found. And the other thing we want to do is to measure with precision the standard model and to test the standard model with as much precision as we can. And what you see here is a global fit to the standard model parameters. On the right-hand side here to the Electroweak sector, on the left-hand side to the flavor sector. And the various bands, the various colorful bands that you see here actually represent, independent measurements, experimental measurements. My contribution to this picture is actually this orange band that you see here. This represents the measurement of this parameter, which is the oscillation frequency of the Bissell-Bess meson that we found at the tevatron in the past decade. And so we made this measurement in a model-independent way. This is a quantum mechanical effect that you see what is the oscillation frequency of the particle, of the system. And then, I measured it to be about 3 trillion hertz, so 3 trillion oscillations per second. Imagine for a moment that instead of 3, we had measured, say, 1.5. It could have been. If that had been the case, then this band, so the radius of this circle here centered there, would be twice as large, which means that this band would be over there. Had that been the case, it would have meant that certainly there would be new physics here. And the reason is that this would really break the standard model because all the other measurements, they sort of are around here, and this one would be away. That would mean that would be new physics contributing to this process. Now, at the end of the day, we did measure it to be 3 trillion hertz for the frequency of the system. That's the number that we measured. And when you put everything together, you see that all these constraints, all these independent measurements, they overlap in this single point there. And so this is a very nice illustration of the robustness of the standard model that allows to essentially accommodate all our measurements to date. So the conclusion is that the standard model is a beautiful and superb theory, and we are happy about that. But of course, there's a number of questions that are outstanding that the standard model does not address at all or do not answer satisfactorily. So this is a list that you can phrase in different ways. Let me just mention 2 of these issues that the standard model does not address. One is this long-standing asymmetry between matter and antimatter that we observe in the observable universe that is related to this phenomenon of CP violation, of which there seems not to be enough in the standard model. The other item that I wanted to highlight, now related more closely to this new scalar that we have found. So it's great that we found a new scalar, but it came and it highlights a serious issue, if you wanted to consider it a serious issue. But the issue is really a fine-tuning in the determination of this mass of this scalar. That seems really unnatural, unless, in the absence of an enhanced symmetry beyond the one of the standard model. All right, so then we have these associated questions, and then what we want to do then at the LHC, it's 2 things. So first, you want to test and to improve our understanding of this great theory that we have of the standard model, and this includes certainly the scalar sector, that the precision is still very limited for now, increase the precision of the Electroweak and flavor sector, and also, of course, the strong sector, and actually probe it in different regimes, and we'll talk about that. So this would be task number 1. Task number 2 would be to actually go beyond the standard model and try to probe and find new physics particles. And for achieving this goal, there's 2 ways of getting there. There's the easy and the hard one. So the most direct way in which you could find new physics would be, in the same way as we found the Higgs, for example, or the upsilon, which would be to, there's new particles that are produced that do not belong to the standard model, and that would reconstruct, and it would appear as a bump in the spectrum. So this would be one way. The other way, and the more challenging in a way, is that we are going to explore quantum mechanics and find the contributions from these new physics particles in processes that we can actually measure with some detail, like true rare decays. So I'll mention both of these later on. For now, let me just tell you what the status of the machine is. So these are the 4 multipurpose experiments. Detectors that we have at the LHC. There's a few more that are more dedicated. But so we've been running the LHC for almost for a decade. And during that time, the collision energy has been increasing from 7 all the way now to 13 TeV. And when you resume data taking in a couple of years, this will hopefully have 14 TeV. But it will not go beyond that. So we'll not keep increasing the energy of the LHC. Now, what we will actually increase is the intensity, if you like, of the beams, and this will result in actually an increase of what you call the luminosity. And if you look into the picture here, the projections or our intention is to actually, by the middle of the next decade, we're going to have a very large increase in the luminosity, in the intensity of the LHC. All right, so we are sitting about here, and what are we doing these days? So there's two main tasks we are busy with. So one is to actually extract and analyze the very nice data set that we've managed to collect at the LHC so far in the past years. And the other task that you're doing is to prepare the upgrade of the detector. And the upgrade of the detector is ongoing now. We are preparing the upgrade that is going to happen in the next decade, precisely to account to our detectors will not be able to really profit from this increase in the luminosity of the LHC unless we would change it. So when we are then improving it, all the detectors are being improved. So indeed, we'll have essentially a new detector. All the sub-detectors for the next decade are going to be, refurbished or actually completely redesigned. And I'll not say many things about that. Let me just highlight here one detector. This is this timing detector. This is a new detector that we are adding, both to Atlas and to CMS. And that is crucial for the high luminosity scenario. And let me say why. So the challenge that we are trying to address here in preparation for this high luminosity scenario of the LHC is that by then we expect to have about or up to 200 simultaneous interactions each time the beams collide. And of course, in order to extract your physics results, you want to be able to separate the different, each individual one of these 200 collision points. And it so happens that the spatial resolution of our detectors is not sufficient for you to be able to actually disentangle that. So what this new detector does, this timing detector, is that it brings a new discriminating dimension to the problem, namely the time. So in addition to the spatial resolution of the detector, we'll be tagging in terms of the time of all these tracks. And this will allow us really to recover the sensitivity that we like to have. So this is an example of the challenges for preparing the future that is ongoing now. But otherwise, I'll focus in the remaining of the talk in the physics extraction of the data set that we already have. So this is an amazing data set we managed to collect. It's about 5 times larger than the run 1, which is what the run 1 is when the one used to discover the Higgs. Now we have 5 times more. In fact, if you consider that the collision energy has also increased, this is an order of magnitude increase in sensitivity or cross-section with respect to the previous running period. So this is for proton-proton collisions, but also for lead-lead collisions. So at the LHC, we collide mainly protons, but a month per year we collide lead ions. And there again, we get a factor of 10 more data in the last run. This run actually took place in exactly 1 year ago, in November 2018. And what you see here are the students in Lisbon, following and taking part in this last run of heavy ion collision data. And actually you also recognize here, if the resolution will be better, you recognize here Elisa, who had been a key player there in the data taking in Lisbon as well. Right, so what I'd like to propose to do now is to actually go and tell you a bit some selected highlights of the physics that we've managed to already extract from this data that we have collected. But I need to also mention that the majority of the results that I'm going to show you do not include the full data set. So meaning that you should be expecting new results for the months to come. So starting with the Higgs, so let me summarize here. So what you see on these top plots are the diphoton invariant mass spectrum. On the left we have Atlas, on the right we have CMS. So the diphoton spectrum here, and on the bottom the four lepton spectrum as well. So these are the channels that were used in the discovery 7 years ago. And since then, what happened is that the size of the peaks that you see here, so the number of events that we have for the Higgs has increased. And with that, what we've done, of course, is we have used these statistics to try and to and to measure the properties of the scalar. So the first thing that was done, of course, is to confirm that this is indeed the scalar, so by measuring the spin, and it is indeed the scalar, so that was done quickly. Now, the part that is not so easy, perhaps, is to measure the width of the Higgs. This is challenging, in particular because we do not have the resolution in our detector to be able to probe the very narrow width of the Higgs. So this is done indirectly, but we managed then to get a bound state around here, the 4.1 MeV or so, that is the standard model value of the Higgs. So for the width, things are compatible with the standard model prediction. Now the mass, so the measurement of the mass has increased in precision systematically, and I should mention that so the main channels are precisely the dilepton and the the diphoton in the 4 lepton states, and you see that we've achieved already a quite impressive precision in the mass, in determination of the mass of the Higgs, and it's getting very close to 1 per mil level of precision. So in terms of production and decay, so there's a variety of production modes and of decay modes of the Higgs. All of them are explored. And this quantity that I'm going to use here, this mu parameter, this we refer to as the signal strength. What this is essentially is the ratio between what we observe in the data divided by the standard model expectation. And what you see is then that this overall ratio here is consistent with unit, meaning that data is consistent with the standard model prediction within the 10% level of precision that the current data set allows. So the next thing that you want to do is to actually probe the strength of the couplings of the Higgs with the other standard model particles. And as you know, so the Higgs couples, in proportion to the mass of the particles. So here you see you have the coupling strength. On the x-axis, we have the mass of the particles that you're probing. And things fall here in this linear spectrum across various orders of magnitude. Now, so the first coupling that we measured was to the vector bosons. And then 2 years ago, we got the coupling to the tau. This is the heaviest lepton. Then in the fall of last year, we got the TTH process, so the coupling to the heaviest quark, the top. And finally, also last year, in the summer, we managed to get also the coupling to the bottom quark. So now, if you think about it, the Higgs actually decays most of the time to bottom quarks, to BB bar. And so you'd think that, presumably this would be the easiest, the first way in which you'd find the Higgs. So certainly that was not the case. It was the last one to be found. And the reason is that there is indeed a huge QCD background that mimic this signal. And therefore, in order to get this observation, one needed to combine the variety of production modes and use, advanced machine learning techniques, not only to discriminate, as you do traditionally between signal and background, but also for object reconstruction and calibration. Right. So now, once we discovered the couplings to of the Higgs to basically the top and bottom quark into the tau lepton, so basically to the third generation of fermions, then this effectively amounts to the discovery of a new kind of interaction that comes with the name of the Yukawa interaction, as you know. And so basically, if you have two fermions, they can interact by exchanging the gauge bosons. But now they can also exchange Higgs. And this is a new kind of interaction in the sense that this one does not really come from a gauge principle, right? So this was quite nice to really have the discovery directly of this kind of interaction. But having said that, of course, so I've showed you this graph before, and what we're doing here really is to test the Yukawa sector of the standard model. Precisely that this decay matrix arises exactly from these Yukawa couplings. But nevertheless, what happened here is that we are doing the measurements, but now we have the confirmation that it's indeed the Yukawa couplings that we are measuring. So we arrive at the stage then with run-to data. We basically measured all the major production and decay modes of the scalar of the theory, and then the question is, what's next? And what's next is twofold. First of all, we want to certainly improve the precision, and this will be you'll continue to do this for for a long time, for the decades to come. And the other thing that you want to do, of course, is to also measure the couplings to the missing particles. Okay, and those are this lightest particle, basically the first and the second generation of quarks, and of quarks and of leptons. So in this planning, then the next one that becomes within reach is the muon, the coupling to the muon, and you see that the muon has a low mass, and therefore the coupling is very small. So this is going to be challenging, clearly. But the reason why, of course, we have a good sensitivity for it is that this will be, again, one of these clean signals where we have a bump, a narrow bump on top of a falling spectrum. Again, the dimuon spectrum. So right now we are about around the ballpark of 2 times the standard model sensitivity, meaning that either with the data set that we have collected or the one that we're going to collect in the next couple of years, this one should be narrowed down. So this is for the leptons. What about the quarks, right? So here the situation is actually much more challenging. So you'll recall that I was mentioning about the BB bar. So the coupling of the Higgs to the BB bar was not easy at all. And if that wasn't easy, if you consider the coupling of the Higgs to the charm, that would be much more complicated. And so what you'll need to do there, basically there's 2 approaches that we have in order to try to pin down this coupling. One is what is mentioned here, the inclusive method. Basically, we have the Higgs. The Higgs decays into a pair of charm quarks, charm anti-charm, and then what the challenge would be, to first identify jets, that come from charm quarks. That's, beyond difficult. And then you need to disentangle that from all the other sources of charm that you have in your collisions. So this is one way. The second way is that instead of looking directly for the charm, you allow the charm to actually bind together into a meson, and then if you allow that, then what you're going to have is a very, very clean signature, which is a dimuon that comes from the decay of the meson back to a photon. And so this is a signal that we actually like to study, and you can do this easily. So there is these 2 approaches. Both are pursued, of course. Here we have, this inclusive approach from Atlas, and here we have this exclusive approach here from CMS. The ballpark, you see that we are, in any case, away, still about 2 orders of magnitude away from the standard model sensitivity. So this is a topic that will require quite a lot of data, the full high luminosity LHC data, to try to get this. And you need also the LHCb also to help us here. Of course, I need to mention that the group here is actually involved in this, directly involved in this approach. Now, one thing that can also be done is to try to constrain these couplings indirectly. And this you can do by measuring kinematic properties of your Higgs. And what you see here, this is the PT distribution of your Higgs. So this is a differential measurement of the Higgs. And imagine that this is impressive, that you can get to the stage when we can do actually a differential measurement of the Higgs, as we do, for jets. It's quite impressive. But the reason why we want to do that is that the shape of this distribution, is correlated to the couplings of the quarks. And this is illustrated here, that for different couplings, we have all these different shapes. So in turn, if you actually measure a given shape, you can go and constrain the actual couplings, right? So this is what is done here. So, right, so then finally, there is the all-important self-coupling of the Higgs, that you recall appears in this potential of the Higgs. And so in there, the way we want to do this experimentally is to look for di-Higgs production. We want to reconstruct 2 Higgses in a given event. I mean, this is exceedingly difficult, of course, and nevertheless, so this is clearly ongoing. It's a major, endeavor. That is a long-term endeavor, but in any case, with the partial run-to data, we are in the ballpark of better than an order of magnitude, getting to the order of magnitude close to the standard model sensitivity. And we have also done projections for what we might be able to achieve here with the full LHC luminosity, and there we expect to have a 4 sigma level observation of this process, and with a 50% uncertainty there. So you see, basically this will be, you need to be explored actually beyond the LHC, and it's actually one of the main drivers for new experiments that we are planning, in particular in the context of the European strategy. Right, so this is what I wanted to tell you about the IGs. I'll mention very briefly now about the Electroweak sector in the top. Actually, the only thing I wanted to really tell you is that, I mean, certainly there's a huge number of processes that we are probing. You cannot even read what they are here, but they start, these processes that are, produced ubiquitously at the LHC, and then you come down to processes that are extremely rare, and this spans more than 9 orders of magnitude here. And so what you're trying to do here then is to make precision measurements of these processes and go and try to get rarer processes where the IGs, again here, now it enters as another building block of our searches and of our studies, just as any other particle in the standard model. So this is critical to test the standard model. It's critical to validate your Monte Carlos and basically learn about the standard model and then embed that knowledge into your simulations. And it's also critical then to, for us to be able to understand our data to identify signals that go beyond the standard model. And so this is, again, an incredible picture that we have obtained here. Just a brief few words about the top quark. So, this was found, as I mentioned, at Fermilab many years ago. Now we have come a long ways since then, since the discovery. The LHC is indeed, a top factory, really. So we've measured the top cross-sections, the TT bar cross-sections in various final states and for various energies, collision energies. And so we continue working on that front. The mass of the top is a crucial parameter of the standard model. As you know, together with the mass of the W, it constrains the mass of the IG, so it's a crucial internal test of the standard model. Here, however, just bringing more data is not going to help you reduce the uncertainty that you see here, because this is systematics dominated. So what you want to do here is to have a trade-off and come up with new strategies that a trade-off between the high statistics that we have and a better control of your systematics. So in addition to TT bar production, there's also the single top production. And in fact, there's additional production modes that are rarer and that we are becoming sensitive now and that we are probing. And then finally, there is this so-called flavor changing autocurrents. So these are basically rare decays of the top, extremely rare decays of the top. And to have an idea how extreme they are, you see that currently the data are these red and blue points that you see there, while the standard model lies here. And this is a log scale, so there's quite a few orders of magnitude there. Now, the reason why this is interesting and we are pursuing this actively is illustrated by these shaded colors that you see there. And these are essentially predictions of new physics scenarios that basically increase by a lot the rates of these processes. So the goal here, we know that we do not have the sensitivity for the standard model. Nevertheless, we are pursuing it actively to try to find, something where we expect nothing. So this is a main strategy to find new physics in the rare decay modes. So here I'll go briefly. I just mentioned that we're talking about the Electroweak and the top. So here we have the observation of the associated production of the top and the Z. So this has been observed for the first time last year. This is a main observation for the last year. This is in terms of production. In terms of properties, let me just mention one without going into detail. So what you see here is these spin correlations between the two tops. The way we access these spin correlations is through the angular difference between the two leptons from the decays of the tops there. And the reason why I'm highlighting this one in particular here is that Atlas has detected a nice, a surprising result that have been a hot topic in the last couple of years, and it still is, where you see here that the slope of the data is actually smaller than the one of the simulation. So the simulation is this histogram, the data are the points. Now, in fact, the situation actually has improved. If you bring the CMS data, we do not have such a big discrepancy. And it also improved when the corrections, when the standard model predictions were refined. So the message that I want to mention here is that we are accumulating this huge amount of data. okay, which allows us to make very, very precise measurements. But in order for us to be able to continue to, interpret our data, we need the same kind of improvement in terms of precision to also occur on the theory side. So in the theoretical calculations are critical that they go to the next order, to the next level of corrections to match the sensitivity that we have in the data. Now, we're talking about the top, so really the highest energy scale in the standard model, and now we come to the low energy, to the low mass region. So here, as we talked about, there's many signals that pop out here that you can measure in detail. In addition to that, we continue looking for new bumps in our data, and I'll show you just a few of these. So the latest new particles found at the LHC are these two bumps. This happened also to be the first result that uses the full data set that we have collected so far in run 2. And this turned out to be two members of the B sub C family of states. So this is a bound state of a B in the charm quark, which is so this is very much not explored, and it's very interesting properties that I don't have time the time to tell you about today. But what I wanted actually to highlight is that the story here is actually quite interesting. In fact, it was Atlas that in run one found this bump. So they found one bump there, as you can see very clearly in the data. Then later on, the LHC went to check their data, and they actually found 0 bumps in the data, and then came CMS, and we found 2. Okay, so this is nice. Now, all of this is actually, of course, completely compatible. LHC came out now afterwards also and found these two spectrum, but the lesson here really that I want to highlight is that our detectors are amazing, that we can find new structures and new particles in our data set. But as the data set increases and as we improve our detectors as well, we are able to go a step further and actually to resolve the fine structure of these resonances, and this is it's really incredible. So those were new particles, but we also have other new bumps that appear in the data, and here we have not new particles but new processes, so new decay modes. And I have examples here that are very recent from the baryon sector, from the meson sector, and from the Electroweak. And so these are critical, per se, these are important per se, these observations, but they actually allow us to do something else, which is to actually find additional structure in our data. For example, if you combine the GPSI with the phi, we have found some exotic particles, and so this is the goal, to go ahead also and do this. Good. So now these were, I've showed you just new bumps that we are looking at, that we have discovered in our data. But we also have our good old bumps. So these are, the high statistics modes. This is the upsilon. This is the first particle that I told you about today. It actually has 3 peaks: the fundamental state and the 2 excited states. And we look at other. So this is hidden flavor, and this is open flavor. So we do detailed measurements of this. So why do you do this? It's for many reasons why we do this. So one is to, you do precision measurements to try to understand the standard model better. So this is this main goal that we have. And here we want to understand, for example, these quarkonian processes or states are, perfect laboratories to study the strong sector. There's many things that are not understood about QCD, and this allows us to do that. So we can actually probe also the energy dependence. But there's another reason why this is important, is that these high statistics modes, they are they serve as reference to study rarer processes. So the main goal is to find rarer processes, but in order to actually have robust measurements there, we need to have reference channels and understand this well. The final reason why we want to do this is that these serve also at baseline to study another kind of collisions, and those are heavy ions. So now I'm going to tell you a little bit, I'm going to change gears a little bit. So we were talking about proton-proton collisions. Now let me talk to you about ion collisions. So nuclear collisions at the highest energy. So let me, start by showing you how such a collision looks like. I don't know if how impressed you are, but you should be very impressed by seeing this plot. So what this shows is an actual collision that took place in the CMS detector in November, precisely November last year. And what you see here is that there's a huge amount, so that we have the detector completely occupied, it looks like. So it's an extremely busy environment that you're seeing here. So the question that you want to ask yourself is, can we actually extract anything, any signal out of this mess? And so let me start by reassuring you that yes, we can. So what you see here is this diamond event mass spectrum. You see the same structures. We can reconstruct indeed different signals. Okay, it's impressive. It's a miracle that we are able to extract this out of that mass of collisions. But the detector is just that good. Now the question arises is, okay, so we can do this now, but why should we? Why would we do that? And the reason why we want to do that, as you know, is to probe and to understand the properties of this quark-gluon plasma, of this state of matter that existed, instance after the Big Bang. And the way we want to test and to measure the properties of this medium is to use probes to test those properties. So there's essentially three things that can happen when we have your probe in your medium. So the first thing that can happen is nothing at all, meaning that if we have particles like the photons, the Z and the W, that are not colorful, so that do not interact with the strong, do not couple to the strong force, then this will, traverse the medium mostly unaffected. And so, it's quite nice, and it's a calibration, a critical calibration of everything that we're doing here. Right, so this is the first thing that can happen. The second thing that can happen is that if instead we have particles that have color, meaning partons, so quarks and gluons, and you put those quarks and gluons in the medium, then as they traverse the medium, they will lose energy. And these energy loss mechanisms are crucial also for understanding the properties of this medium. And then the final thing that can happen, and perhaps the most striking one, is that your hadrons, they might actually melt in the medium. And so I like this one particularly, so let me actually show you the results. So first, you see here these three peaks. So these are the upsilon. I showed you this plot before. So this is the BB bar bound state, and it has three states. It has three states here: the fundamental state and the excited states. So when you do the analysis in proton-proton collisions, you see these three states very nicely, as I've showed you before. Okay, so this is great. So this is actually my first analysis with the LHC data. My second analysis with the LHC data was to repeat that analysis of this BB bar state, but instead of using proton-proton collisions that we had at the beginning, we used lead collisions. Okay, so you just repeat the same analysis. And here, and you can see the results exactly there. So these are the data points that you see in this plot. And if I ask you, what do you see here? I think it's very striking, and I'm sure if I would ask you, you'd reply. So there's two things that you can see here. One is that you see that that in lead-lead collisions, the data is very much suppressed compared to proton-proton collisions. So something happened to your states that they sort of melted. They were suppressed in the medium. Okay, so this is one thing. But there's another thing, and that is perhaps that is actually more striking. And I hope you agree with me. And that is that this suppression, this melting, is not universal. Actually, it's sequential. It depends. So you see that the excited states here are basically the third one is completely gone. So this one that you'd expect to be like that, as we see in proton-proton, it's not there at all. And the second one is basically very much suppressed as well. It's almost not there. Okay. So the two things that happen is then there's the melting, and then on one end of every single one of the states. But the second thing that happens is that the excited states are more melted than the ground state. And so this has to do with both of these methods have to do with the color screening. Basically, that the BB bar is going to interact with the medium, and then this will really melt the states. So, which means that if you go and we measure the suppression of a variety of states, this will give you indication of what is the effective temperature of your QGP, right? So this is the thermometer of your QGP is provided by these querconium states. Good. So this is, I believe, the most striking effect, that things do melt in the medium. And then the second process that I mentioned to you then is this energy loss. So the partons, as they traverse the medium, lose energy. This is this is what you expect, and this is what we see in data. So this y-axis here shows you the suppression factor. So you see that everything is below 1. That means that all hadrons are suppressed in nuclear collisions compared to proton collisions. But that's which is great, and that's what we expect. But then again, there's something more striking than that, which is that that suppression is not universal. And here, so while in the melting, you recall the actual relevant variable was the binding energy of the quarkonia. Here, the relevant variable is actually the mass of the particles. So the most massive particles lose less energy than the other ones. So the B lose less than the D, and then the lighter hadrons lose most energy. So now, as it turns out, now for the first time, we are able to go a step further and actually disentangle these different components, and actually go a step further still, and we actually measure the actual hadrons, the actual identity of the hadrons. And this is achieved for the first time with the LHC, and the latest that have been observed are the B mesons. Okay, so you have the B plus, and here we have the B sub S, and this is the first time that we are able to reconstruct this anywhere in ion collisions. And this is great. And now what it allows us to do is actually to do something more, that once you start identifying the different parton species, hadron species, you can compare them. And for example, if you compare the B sub S with the B plus, and this is preliminary results, you see that in ion collisions there seems to be not a suppression as we've seen before, but an enhancement with respect to proton-proton collisions that are seen here. And this is the so-called strangeness enhancement, is again, an expected QGP signature. So this is novel probes of the QGP, and I've myself been working with this. This is my student that just graduated with this measurement. And now I wanted to mention just very fresh results from the last couple of weeks. The papers are actually not out yet. They are being interned. The results are out, but the papers aren't yet, so we need to wait a couple of weeks still. And so these are the last two, the most recent observations that we have. So first, we found for the first time the top. So before I told you the bottom quark was found, in the QGP, and now we have the top also being reconstructed in the QGP. So this is one thing. The other one is very exotic. So we have found, and this is this peak that is here, okay? So this bump that appears here is a bump that has been found in non-nuclear collisions before, actually by Bell in 2003, and it has been established by everyone. So all experiments have, essentially many experiments have detected this bump, either in lepton collisions or proton-proton collisions. Now, for the first time, we find this bump now in nuclear collisions. So, in the case of the top, we'll be able, not now, but when we're going to have much more data, maybe in another machine, we'll be able to actually probe the time formation of the QGP using the top. While for this one you can do two things. I mean, one is to try to understand the properties of the QGP, but in particular, what you can do is to try to understand the properties of the X itself, because we do not know what the nature of this particle is, and probing it in a different medium, actually, which is a strongly correlated medium, might be able to help. So this is, two main highlights from CMS just from weeks ago. Okay, so I'm entering in the last thing that I wanted to tell you. I don't know how much time I have because the clock is not running. But so what I wanted then to conclude this presentation with is to tell you about then the searches for physics beyond the standard model. Again, so there's two ways of doing that. The easy and it's not easy, trust me, but let me call you them the easier way of finding new physics. The first one would be then, as I mentioned, to find new bumps in your spectrum, right? They do not need to be bumps like that. They can be other. This does not need to be the mass. Can be other variables. But this would be the easiest way, or the most direct way, that you have your collision at the LHC. You produce this new particle that does not belong to the standard model, but it will decay somehow to standard model particles or whatever, and you can find it. So this would be one way. And So indeed, what you would expect, so here we have the dielectron invariant mass spectrum, here we have the dijet invariant mass spectrum, and what you would expect, would be for having these bumps appearing on top of your data. Now, as it turns out, and we have looked into many of these spectra and many variables, there is no significant excess, so these bumps seem not to be there. So what this means is that whenever we do not see the bumps there, what you do is that we exclude the scenarios that could give rise to these bumps. And here I just summarize, not even that, I just illustrate here, the exclusion of the various scenarios that we have. I classify here this, normal sort of beyond standard model physics. This would be, signatures with missing momentum, like most of the SUSY, vanilla SUSY. Then there's more exotic stuff, like extra dimensions of space of different kinds, or new heavier gauge bosons. Are we locked? You have to stay. That's interesting. All right, that was intended. Right. So this is the. So we have the normal BSM, we have the exotic one, and we have the very exotic one. Let me say a few words about this very exotic kind of way to look for new physics, in which I've also been involved. So this is this so-called long-lived new physics particles. Let me just mention the following. I mean, so why is this interesting? So we've been looking for new physics in a given way. So this easiest way in which you expected to find new physics when you turn on the machine, I mean, this did not really happen. So what we are trying to do now here is to find alternative ways to see if perhaps new physics is being produced all the time at the LHC, but somehow we are missing it, right? Simply because they have different signatures from what we anticipated. And such a striking signal that could happen is that imagine that that your new physics particle actually has a long lifetime. So what that would mean is that the particle will be produced in the collision, in your proton-proton collisions. Okay, you're right, you have your new physics particle there, but then it goes, and because it lives a long time, it will travel quite a distance in your detector. So in that case, with the normal reconstruction, normal algorithms that we have in our detector to make sense of our data, this would be completely missed, because typically we expect that particles come from the point where they were produced. And so this is challenging, but if you go and you actually perform the analysis with dedicated reconstruction algorithms and so on, this becomes a very clear signature for new physics, and an explanation why we haven't actually seen it. And so one way is then to look for these highly displaced vertices in the detector. So this is a production vertex, this is a decay, and so we start the reconstruction in this point. And when you do this, then again, we do not find any excess again, but we are trying and keep going on. And then we place limits not only in the mass, as I've shown you before, but in terms of the lifetime of the particle. So I should say that I was involved in in this first generation of such searches, and now this became really popular. And it even comes with the name of the lifetime frontier. And this makes sense, right? If you do not find new physics with your more traditional kind of scenarios, then you go and you really pay attention to alternatives, and that's what you're doing. What's the goal? The goal is to leave no stone unturned in our search for new physics. Good, so this was the direct search for new physics particles, in a more standard or less standard way, but then there's the second way that we have, the second approach that we have, and that's what I'm going to talk about now. And so what we want to do here is actually, to use quantum mechanics here to our benefit, and the idea is that, so if we have these new physics particles that do exist, then they will contribute. So quantum mechanics allows, and actually they must contribute to the amplitude of processes that you can measure. Typically these are rare processes, and so by studying rare processes you can indirectly test the presence of these new physics particles. The advantage, by the way, with respect to the direct way is that even if the mass or the energy of these particles is very high, so high that they cannot be produced directly, actually we keep sensitivity to these particles. And this was actually traditionally how new physics was first found. To illustrate the point better, let me present to you this golden mode. Some of you have already seen perhaps each of these two processes separately, but not placed together. I like to place it together. So this is the BCBS system. Okay, it's a quark-anti-quark system that we've seen before. And there's two processes, two extreme processes that take place here. One is that this amazing fact that if we have your particle, it spontaneously transitions into its antiparticle. And it does this, as I said before, a trillion times per second. This is pure quantum mechanics, and it's amazing that this actually happens. And you see it's extremely fast, so this is an extreme process. The other extreme process is that this meson can decay to a pair of muons, to a pair of leptons here, but this is actually very, very much suppressed in the standard model. This is not, in the standard model, this is very much suppressed for a variety of reasons. And now, so you see here that we have actually two processes, the mixing and the decay. Both were actually observed. This was, my thesis in the past decade. This one we just did 4 years ago. Here we have this BCBS peak there that corresponds to this decay. This is the diamond invariant mass spectrum, as we like. But so this is, extremely fast and extremely rare and extremely sensitive to new physics. The reason why it is doubly sensitive to new physics, as I mentioned, is that, new physics can contribute to one, to the other, and in the interference. So this we've done a decade ago. This one we are doing now, and now we are starting to couple them. So let me tell you what the status is of this, the decay part. So here we have the data. This was from 4 years ago when we detected this particle, and this is the most recent result that we've just submitted for publication. What you see is that the data are these contours centered in this point, and the standard model, you almost don't see it, but it's there. Okay, it was there, now it's here. So what you see is that, somehow this is compatible with the standard model. This is only the 1 in 2016 data, so we have much more data to analyze, and we are going to decrease the uncertainties here and see what happens. So this is when you compare to the standard model. For now, as usual, we get compatibility, but the goal is to improve precision. The other thing that you can do is to compare to new physics, right? And when you compare to new physics, you see that actually we exclude huge chunks of the parameter space of these new physics scenarios. For example, here, these are some new physics models in the flavor sector. And here we have supersymmetry, where this yellow part of the parameter space there is completely excluded. Now, so if you go back to this process, so you have the mixing, we have the decay that I just told you, but now we can actually have the coupling. The first means by which you can have this coupling is that, in fact, this decay, okay, of the B into two muons can actually only happen for one of the two states that describe this system. Only the heavy of the two states that is here can actually decay, the other one cannot. And so by measuring actually the lifetime of this B to mu mu, then we can access additional sensitivity to new physics, and so lifetime is a major goal that we have here. So this is the first measurement by LHC. CMS just released it a few weeks ago, and so this is the first, proof of concept, if you like. We can do this, but we do not yet have the sensitivity to find new physics there. But here we have a projection that we also did in Lisbon, where we have, this is what we expect with a full run-to data set. In addition to the BCBS, we should be able to find the B0 and measure the lifetime with a 3 precision measurement, and there we can gain sensitivity to new physics. Right, so we arrive at the situation that, either with direct searches or indirect searches, the standard model seems to be extremely robust. It's a beautiful model. It sort of accommodates everything. But now let me emphasize, to finish, something that appears in the data, and it might very well be the way in which you are going to find new physics at the LHC. And so what we have here is that, we do not have a single measurement that deviates significantly from the standard model, but we have actually a variety of measurements where small deviations are found. Once you try to interpret these small deviations in a consistent model-independent way, then actually we get a deviation from the standard model, okay? So this is perhaps, a good chance that we might be able to find new physics, is that we're going to do lots of measurements, and then we try to combine everything together and see a coherent pattern showing the presence of new physics there. So let me illustrate what the situation is now, but this goes beyond what the situation is now. This is, a means by which new physics might be revealed. So these so-called flavor anomalies, as they are referred, this is the most exciting topic, in the last couple of years in the ING physics conferences. So there's two parts to it. The first one is these transitions of B to S transitions, okay, opposed to leptons, and this is like the B sub S to mu that we've seen is this transition. But there's other processes that realize this transition. And there's actually many variables that are sensitive for different kinds of new physics. Now, among the many variables and processes, the first one where deviation was found, and this was by LHC, was this so-called, this is an angular parameter that comes with the name of P prime 5. So what you see there is that the data overshoots the prediction. The prediction is these yellow boxes. The data are the data points there. So this by LHC and then corroborated by Bell and by Atlas and so on. So you see that there is indeed some deviation there and that it has persisted there. Now, what happens here also is that the uncertainties are large, and so we've done is a projection for the full luminosity of the LHC. Then we'll be able to shrink these large arrow bars to these small boxes that we have here. So this will be resolved. At least from the experimental side, we'll shrink here the uncertainties there. So this is one piece. The other piece, as I mentioned, is that there's many, so in addition to this P prime that you mentioned, in addition to the B sub S to mu that I mentioned, actually there's hundreds of measurements that are done and that we can actually compare against theory. And here you see that there's some systematic deviation between the data and the theory bands. Now, none of them, as I mentioned, is actually very significant. There's no 5 sigma discrepancies here in either of them. But now, the catch here is that you're going to have a model-independent theoretical framework in which you try to interpret all this data at once. And when you do, then you actually find a very significant deviation. So in this plot, and you might not see well, so the standard model is at the center here of the origin of the plot, and the data is there. And so this is 1, 2, 3, 4. So 4 to 5 sigma deviations there. Okay? So you see the miracle that is happening here. So here is like 1, 2, 3 sigma many deviations, but then they are not random, right? Because certainly you can have statistical fluctuations. But here the indication is that this is not statistical. This might be a systematic deviation that you can interpret coherently, and then you obtain new physics revealing to yourself like this first before you get the strong deviation there. So now the other half of the so-called flavor anomalies is that you can still use this same transition, B to S lepton-lepton, but what you're going to do here is that you're going to compare different lepton flavors. So for example, you have this decay, B to K plus a lepton, plus a pair of leptons, but you compare this decay with muons with this decay with electrons. Then you compare the rates of these processes. And when you compare the rates of these processes, what you expect in the standard model is that this is 1. This is because the standard model does not distinguish between flavors. This is flavor universality in the standard model. So electrons and muons have the same couplings to the W. And then you expect this to be 1. Good. So this is what we expect. But what we see in data, and data is is reality. So this is from LHC. You see that LHC saw so the measurement actually lies significantly below this line. Okay? And this was done for different decays, and they consistently are below the line. So this is the lepton flavor universality comparing electrons to muons. But then you can do a comparison now with the taus to electrons or muons. And here you use these decays, these transitions, not B sub S, but rather B to C. This is actually much more, the other one was rare, this is not rare, so there's plenty of data like that. But it's actually extremely challenging because it involves taus. Taus, it's a very difficult object to actually reconstruct in hadron collisions. And so the first place, so the first experiment to actually see this discrepancy was were the B factories, was Babar. These are the results from Babar. Bell, which is the other B factory, also saw a discrepancy. And you see, if you combine both, this is where the data lies. In this parameter space, this is where the data lies. And this is the standard model. And again, you see that it is 1, 2, 3, 4 standard deviations above. So you see that there's different kinds of measurements in different kinds of transitions where new physics seems to be playing a coherent role in leading to these discrepancies. So this comes with the name of flavor anomalies, very exciting topic. And of course, our theoretical colleagues have been very excited about this discrepancy as well. and their conclusion is that the most favorable scenarios of new physics that could explain these anomalies are either new gauge bosons like Z primes, or something more exotic, some particles that contain both lepton and quark quantum numbers, referred to as leptoquarks. So these are the preferred models, and now what we can do at Atlas in CMS actually is to go and actually to try to find these particles, these Z primes, these new gauge bosons, and these new beasts here, the leptoquarks, and you can try to find them directly. So what you see in both of these plots are the couplings on the y-axis and the mass of these new physics particles, the Z prime and the leptoquark, on the x-axis. And what you see is that in this parameter space there is this region that is favored by the anomalies. This is where the anomalies lie, okay, in this case, and here is this blue cone. And by doing this dedicated direct searches, now we are able to probe, at least here in the low mass region, we have the sensitivity to start probing and removing and excluding the presence of anomalies here at this mass. Which means that if it's going to have higher mass, then we'll no longer be able to be sensitive at the LHC. You need other machines, but here we have some projection that for this case, with the full Anomalies at the LHC, we are sensitive up to 1.5 TeV leptoquarks. So, to summarize, so we have, in general, there is no deviation from the standard model. If you look in detail, we start having a pattern of coherent deviations. These deviations are found in the indirect searches for the standard model, but then you can actually go and also look for these new particles directly, and that's what you're doing. Okay? And so the story so far is there. We need more data to go ahead, and now I arrived to my conclusions, and I hope that I told you and convinced you that the LHC the experiments are providing a wealth of beautiful, precise, rich results. I've shown you just a very small personal highlight. So we are testing the standard model, trying to understand the standard model to better precision. Certainly the scalar is the main priority for the field in the years and the decades to come. This is a very special particle. Also the Electroweak in the top sector and the strong sector as well in different regimes. And then, in addition to testing the standard model, we want to find evidence for physics beyond the standard model, and you do this either directly or indirectly. Directly, there's no clear evidence for a significant departure from the theory. Indirectly, there is this tantalizing coherent set of evidence of 5, if you like, actually it goes to 5 sigma light kind of evidence, but it's not done in the direct way. So data will tell us, and just remember that you have just a very small fraction of data of the full LHC program that we have on tape and that we can analyze. Okay, thank you very much. Questions?
Okay, so for the old people like myself, so we were used with the idea that discoveries were made on hadron colliders and precision measurements on lepton colliders. But it seems you spoke several times about the precision, and we know that we have reached an unprecedented level of precision. So, in your opinion, this kind of a model, law, that precision is made on lepton colliders is over?
Well, certainly precision measurements are easier at lepton colliders. But so at the LHC, so at the Hadron Collider, we are indeed entering a precision era, and certainly things are tougher there. But actually we can do it, right? So and there's two ways of getting there. So it's through very detailed precisions and to getting actually also rarer processes. So this becomes in between precision and actually discovery. So when we have this, although we are not increasing the energy of the collisions, we are increasing the amount of data that we have, which means that new physics can be there, but being just very rare. right? So because the couplings to the CERN model are very, very small. And so, you know, if, you see that, so the situation is we do not have new physics so far, at least clear. There's a few possibilities why this is the case. One is that, as I'm saying, it is very, very tiny couplings. And if it's very tiny couplings, then the strategy, of course, is to go and accumulate more data so that you can actually probe these very rare processes. So this is one way. But the other possibility is that actually the new physics has higher scale. It's heavier. And as I mentioned, we are not going to continue increasing the energy of the LHC. However, we retain the sensitivity to those heavy particles through these indirect measurements. So we are in a situation that we do not have, you know, a smoking gun for where new physics are. If you either then this flavor anomalies that we are discussing, but this data of the LHC should be able to point us in the right direction, and then we'll be more in a better position to go and move to the next stage, which would be, you know, a lepton collider to find something specific. As you know, otherwise we are in the discussion of the machines that are going to replace, that are going to come after the LHC. In Europe, this is the time that we are really having these active discussions because we are updating the European strategy for particle physics. And indeed, the decision that we are converging on, you know, is on after the LHC is going to be a lepton collider, either circular or linear, but this will be a lepton collider. And for there, but the reason there is to do precision measurements of the Higgs, and again, to find if this is the Higgs of the CERN model or not. So new physics can be either hiding in many different ways, and first we address it with a hadron collider to try to find new physics, you know, indirectly in the ways that I mentioned. Otherwise, we go to the precision Higgs, which is the next step, and then we have to reassess where we are. But I agree with your comment. I mean, hadron colliders are discovery machines. We haven't found it in the easier way, but we keep looking for the beautiful data that we have to find new physics in this way.
No. Thanks a lot again for your talk. It's very nice. Because the LHC program stayed in the long shutdown now. It started the next year. And what's your opinion concerning what is then the raw topic for the run 3 in the LHC?
Okay, that's a personal question. So that believes on. I mean, this is mostly to do with your taste. I mean, certainly. I mean, LHCb is leading the flavor anomaly discussion, and we are very. We are in a situation where, you know, that LHCb is actually seeing overall the closest evidence that we have for new physics, and. But this is unusual that only one experiment is doing it. So a main focus that we have, and also for N3, is to try to find ways of you know, collecting data so that we are able to actually test the LHCb. So independently, right? Because certainly LHCb will have more data, and they will be able to clarify the situation. But what is missing there is an independent experiment with different systematics, right? So this is one way in which we are pursuing. The Higgs is certainly a major topic as well. There's this couplings that are just around the corner. We want to see if it's there. You know, if it's there, then it's just a matter of precision, and for that we need a lot of data. But imagine that it's not there. Then we're excluding, right? And that is a big deal, right? So maybe that's not the Higgs. So the Higgs is still a very hot topic. But then I agree that otherwise, in order to do this, these direct searches for generic scenarios, because you are not increasing in energy anymore, so it will take long to get sensitivity to, you know, to advance in excluding the parameter space of new physics. But this will be certainly done as well, because as you accumulate more data, you effectively gain more, you know, effectively gain access to the tails, and therefore to higher regions. So, and then there's heavy ions, which is an amazing field that is, is being driven completely by experiment. We don't really understand much on what's going on there. There's a very little revolution in the field of heavy ion physics. And this is QCD, and QCD, it's a central part of the CERN model that we need to understand as well. So there's lots of possibilities, and for the younger people in the audience, I mean, the beauty of working in an experiment like this is that you can do many different topics, and you can actually do several different topics, and we do that, right? We do one, we move to another one, but otherwise, it's your choice, it's your personal choice of, it's your bet as a researcher to see what's the best. So as you know, we are looking into the Higgs of the couplings together, and we are working on the flavor sector as well.
Thanks again.
Thank you.